Okay, can you see them?
Yeah, very good. We can see that.
Okay.
So let me just start with a very informal introduction. Of course, Professor Luiz Davidovich needs no introduction to members of our community here, but still I must say that say a few words about him. So he's a Professor Emeritus of Physics at the Federal University of Rio de Janeiro since 2021. And he has spent his life in various positions around the world, Rochester, then Zurich, so on and so forth. And he has, of course, many awards and recognitions to his credit, like fellowships of various societies, Optical Society of America, American Physical Society, Third World Academy of Sciences, and is now the president of the Brazilian Academy of Sciences as well. And he has got many awards for his contributions. He was awarded the Brazilian Grand Cross of National Order of Scientific Merit in 2000. In 2001, he got the Physics Prize of the Third World Academy of Sciences. And 2010, he got the Admiral Alvaro Alberto Prize awarded by the National Research Council for Scientific and Technological Development. Professor Davidovich's interests span a vast area of quantum optics and quantum information, and he has made several major contributions in this field, for example, in the areas of decoherence entanglement, laser theory, quantum metrology, dynamics of quantum coherence and quantum entanglement, so on and so forth. So he has made many proposals for experiments, and some of which have also been carried out by his group. And so today he will be talking about recent advances in quantum metrology. So Professor Davidovich, you are welcome to begin your talk.
Thank you very much, Professor Majumdar. It's a big pleasure for me to be here, at the internet talking to you. I have been to India, I think, 3 times, and these were great experiences, actually. I really enjoyed that. Once was in a TWAS meeting in New Delhi, and then that's when I got the prize from TWAS, which I spent traveling through India. I really did want to know about India. So it's a big pleasure to be here, and I say hello to all of those who are attending this meeting. It's not so early in the morning now. It's about 8:30 a.m. So it's a civilized time. It's a civilized time. So I'm happy to be here. So I'm going to tell you about recent advances in quantum metrology. First, I'm going to make a review of this field, and then I'm going to tell you about some new results that we have obtained in this area of quantum metrology. So you see, if you look at quantum technologies, which have really developed at the end of the 20th century, they have 4 important pillars, which are shown in this slide: quantum communication, quantum computation, quantum simulation, and sensing or metrology. And all these pillars are purposed, as you can see, by important ingredients like engineering and control, software, theory, education, and training. And they are based, they are stepping on some very solid basic science. So that's a field which combines visionary applications with some very interesting conceptual aspects of quantum physics. Today, I am going to center on quantum sensing and metrology, and that has to do with parameter estimation. Now, you may be interested, for instance, in the depth of an oil well. That's not a quantum mechanical problem, it's a classical problem so far. And how can you find the depth? Well, you send a probe. The probe may be sound waves, and by looking at the return of the sound waves, the reflection, the waves that are reflected by the oil, you can get information about it. So in this case, sound waves are the probe. You may be interested in the time duration of a process, or in the transition frequency between 2 levels of an atom. Just to give you an idea of the extreme precision obtained in this case, This paper, which was published in Science in 2010, shows that they were able to measure, that was David Wineland's group, they were able to measure a frequency, a difference in frequency between two positions of an atom in the gravitational field of the order of, with an uncertainty of the order of 10 to the minus 17. It's a relative uncertainty. Now, this difference in frequency is caused by the different positions in the gravitational field. So that's a measurement related to general relativity. You can also measure some very weak forces or some very small displacements on, for instance, a mirror, which is here. And you can detect this, and it's important many times to detect this with a very large precision. You can detect phase displacements in the interferometers also with a very large precision, and the probe in this case is just light. And of course, you may have heard about the laser interferometer, gravitational wave observatory, LIGO, and more recently, that started actually in 2013, they were able to show that squeeze states may enhance the sensitivity of the LIGO gravitational wave detector, and this is being used nowadays. Squeeze states have allowed the LIGO gravitational wave detector to look at even further directions in space. So that's a beautiful example of the use of quantum physics to probe the universe. So these are some examples. And more recently, quantum sensors have been built even by some companies and also in several labs. For instance, you can use a single atom to map the structure of a biomolecule. You can use magnetic sensors for brain imaging. Gravimeters have been built by companies, they're selling them. They are based on atom interferometry and then can detect small gradients of the gravitational field, and that can be used for surveying underground water and oil. Gyrometers and accelerometers are very interesting also because they lead to GPS-free navigation. The idea is the following: suppose you have a submarine and you know the initial position of the submarine, then if you follow all the accelerations and the rotations of the submarine a long time, you can know where the submarine is after some time. So you can do navigation without using the GPS, which for submarines is especially important. Atomic clocks have been built with a systematic uncertainty below 10 to the minus 18. You know, that was something unthinkable some years ago. So that's a very high precision. And you might wonder, you know, why do you need that? Well, you know, with this kind of precision, you can use the GPS to find an object with an uncertainty of 1 centimeter. And that's, of course, is very important for these new cars without drivers, you know, automatic cars, automatic trucks that don't need drivers. If you have 10 to the minus 16 instead of 10 to the minus 18, the uncertainty in position is 1 meter. So that means clearly disasters for automatic trucks or cars. So you really need 10 to the minus 18 to have an uncertainty in the position, which is about 1 centimeter. So that's some of the examples of quantum sensors. And in fact, this area of quantum sensors and quantum metrology is very much pursued nowadays, both in academy and in industry as well. It may be one of the first successful applications of the new quantum technologies. Now, there are some important questions related to this area, and the questions are the following. First, what are the ultimate precision limits in the estimation of parameters according to classical physics and quantum physics? Are there fundamental limits? Is quantum mechanics helpful in reaching better precision? how to cope with the deleterious effects of noise. And then, if you use quantum physics for metrology, there are also important questions. What are the best possible measurements? What are the best incoming states in order to get better precision? Is it possible to find general bounds and strategies for reaching them, which could be applied to many different systems? So these are the basic questions, the basic challenges of this field. Now, either in classical or in quantum metrology, the strategy is like the one I show you now. You first prepare a probe in a suitable initial state, that's the blue ball here, and then you want to explore a dynamical process. You want to estimate a parameter characteristic of a dynamical process, so you send the probe through the process to be investigated. Then you have a final state of the probe, which depends on the parameter. And then you choose a suitable measurement of the probe and associate to each experimental result an estimation of the value of the parameter. Okay, so that's the usual situation in parameter estimation. And we are going to show you how to mathematize it, how to turn the description into some explicit formula. Now, this was done a long time ago by Kramer, Rao, and Fisher. So these are the guys who initiated this field. And in fact, they showed, first Kramer and Rao showed, and then Fisher added some important properties to this, is that the uncertainty in the estimation of a parameter X, which could be a coupling constant, could be a gravitational field, for instance, is bounded below by this quantity here, which involves the number of repetitions of the experiment. So the uncertainty decreases with 1 over square root of n. But then there is this other function here, which is given by this expression. You can express it in several ways. I prefer here to express in this way. And this is so-called Fisher information. Now, these p's that you see here are the probabilities of getting an experimental result k if the value of the parameter is x. So this corresponds to actual measurements. And k's are the experimental results, which depend, of course, on the set of measurements you are going to adopt. Now, Fisher showed that this inequality can be saturated. That is, it can be transformed into an equality for Gaussian states or when the number of repetitions goes to infinity. Also, if you look at this expression here, you see that the Fisher information depends on this derivative of the square root of the probability with respect to the parameter. And this derivative is like a speed. It's a speed of change of the square root of the probability when the parameter changes. So you see that the faster the speed, so the larger will be the Fisher information, and the better will be the precision, or at least the lower bound of the precision. And this is hinting at us that the precision increases with the distinguishability of the two probability distributions obtained experimentally. The probability distribution when the parameter is equal to x, and the probability distribution when the parameter is given by x plus delta x, some small deviation of the value of the parameter. Now, all of this is valid for the so-called unbiased measurements. That means that the average of the measured value of the parameter should be equal to the true value of the parameter. And also this uncertainty here is just the square root of the variance with respect to the average, okay? So this is the magic formula of Kramer and Rao. I'm not going to derive it here, no time for that, but you can find that in many books on quantum metrology. Now, if you have continuous measurement instead of discrete measurements, then you must replace the sum here by an integration, where now this psi here is the possible values of the experimental results, okay? So we are going to base our talk on this expression here, or on this expression here for the continuous case. Now, let's try to understand the Fisher information a little bit better and have some intuition about it. So the Fisher information is related to an important question, which is the one written there. How much does the outcome probability distribution of an experiment change by a change of the underlying true value of the parameter? Now, the distance between two probability distributions, say P of k for a given set k of outcomes, corresponding to two different values, x and x prime of the parameter, is given by the Hellinger expression, which is the one you see here. Okay? So this defines the distance between these two probability distributions, which you see correspond to two different values of the parameter. Now let's make a very simple calculation. We set x prime equal to x plus dx, and then we expand this in a Taylor series. And I leave it to you students to show, it's very simple to show, that if you do this expansion, you find that this distance here is given by this expression here. That's just the derivative of the square root. And this is precisely the Fisher information which we found before. So you see, the distance between these two probability distributions is given by this expression here. So indeed, now if you define the two sides of this expression by dx squared and take the square root, you see that square root of f of x is really the speed of change of the probability distributions. So f of x, the Fisher information, is a measure of change of the probability distribution. Okay? So that's the, if you want, the geometrical meaning of the Fisher information. It tells you how far away are two probability distributions if you change the parameter a little bit. And that affects the precision, of course, for estimation of the parameter. Now, let me give you an example of that, looking at optical interferometry. Now, you have an interferometer here with two arms. These are mirrors, and then you want to estimate this phase here. Okay? So the idea is that you measure, you throw light onto the interferometer and you measure the light afterwards. Now, one criterion to find the precision is to find the scalar product between a coherent state, suppose you use a coherent state to estimate the phase, and a displaced coherent state, a coherent state which has a phase a little bit changed with respect to the previous one. This will give you an idea of how far away are these states if we change the phase of the incoming of the probe, if you want, a little bit. Now, this scalar product can be calculated. It's given by this expression here. And if the change in phase is very small, you can expand this exponential and find that the scalar product here is given by this expression here. So you see, if delta theta is of the order of 1 over square root of the average number of photons, this scalar product will be equal to 1 over E, which is a criterion for saying that the two states are far apart. So this defines the precision in this case. You can really distinguish one state from the other, and this gives me the precision in the estimation of the phase, which is just the inverse of the square root of the average number of photons in the coherent state. Now, this is so-called standard limit, the short noise. Now, you can increase this precision for the same average number of photons. Use the so-called noon states, which is a state like this. You see, it's called noon because you can read noon here. So it's a state which has n photons, either in the upper arm or in the lower arm of the interferometer, but you don't know where they are. Okay, so it's a superposition of the two situations. Now, if you consider this change in phase in the upper arm, it will affect only the photons that are in the upper arm. So this state will become this one here. So this is just the previous state with now a small change in phase. Well, I have written here theta instead of delta theta. Just assume that theta is very small. Now, we can now find the scalar product between the two states, the noon state and the nu state with a small phase change instead of theta, a delta theta. And that's very simple to calculate. It's given by cosine square of this expression here. And you see that cosine square vanishes when delta theta is equal to pi over n. So in this case, this defines the precision. The two states are actually completely separated if the change in phase is pi over n. This change could be very small if n is large. And therefore, we can define the precision as of the order of 1 over n, where n is the number of photons in the state. So you see, we consider that we can distinguish the two states, in this case when they are orthogonal, and that gives us the precision in the estimation. So we can really recognize that the two are different. So we can, by doing that, we can calculate the precision in the estimation. Now you see that for the same number of photons, the precision is better in this case. It's now 1 over n instead of 1 over square root of the average value of photons. So precision is better for the same amount of resources, which in this case is the average number of photons. And this is the so-called Heisenberg limit in this case. So you see, that's just an illustration to show you that quantum mechanics helps. Actually, coherent states are in the limit between the quantum and the classical world. They are very classical in some ways. So they are the best you can do by considering almost a quasi-classical state. And you see that what you get there at most is the standard limit. If you use really an entangled state, which is this one, a state which has photons either in the upper branch or the lower band, or the lower branch, you get a better precision. So quantum mechanics can help. Now, another remark which is important, this looks like a Heisenberg uncertainty relation, right? Between the phase and the average number of photons. But of course it is not. You don't have a phase operator here. The angle for us is just a parameter which we want to estimate. And we're going to elaborate on this point a little bit more. So parameter estimation, in fact, can give you some light on the meaning of some uncertainty relations, like energy-time uncertainty relation and number phase uncertainty relation. In fact, for us in quantum metrology, these uncertainty relations are not the usual quantum mechanical uncertainty relations that come from the commutation of two operators. Okay? Here, they are relations that involve parameters. In this case here, the time-energy uncertainty relation, time is a parameter. Here, phase is a parameter. So that's a big difference between quantum metrology and Heisenberg uncertainty relations. And I find it much more convenient to consider that these uncertainty relations really are Kramer-Rao uncertainty relations and not Heisenberg uncertainty relations. Okay, so I have shown you some examples of the usefulness of using quantum states for estimation. I have told you about Kramer-Rao relations for quantum for metrology. In fact, that was classical metrology. You just measure the probabilities of getting some experimental results if the value of the parameter is X. Now I want to generalize this to quantum metrology. In fact, we can define a quantum Fisher information in the following way. We define first the Fisher information for quantum mechanics in the same way as before. Here I have the continuous version of that. Now, remember, P is the probability of getting an experimental result psi if the value of the parameter is X. Now, in quantum physics, this probability is given by the average of some projector, which I call E of C. And these projectors must satisfy the relation that the integration or the sum of all of them must be the unit. So you cover the whole spectrum of projectors. And more generally, these operators here can be something more general than von Neumann projection operators. They are POVMs, that means positive operator value measures. And this is defined as a set of positive semi-definite Hermitian matrices on a Hilbert space that sum to the identity matrix. So of course, this must be larger or equal to 0. That's a property of these operators, like the von Neumann projection operators. But here they are not necessarily orthogonal. A special case of POVMs is the von Neumann operators, and they satisfy these relations here. So that means that they are orthogonal, but in general, these measurement operators don't need to be orthogonal. Now, what I have just shown you corresponds to a given quantum measurement for this chosen set here of operators. Now, the ultimate lower bound for the estimation of a parameter is obtained by optimizing this expression here over all possible measurements. So over all possible sets of POVMs. And then this gives us the maximum value of the Fisher information, of the best measurement as well. And that defines the quantum Fisher information. It's the maximum of the Fisher information over all possible choices of these projection operators or POVMs. So this is the quantum Fisher information. So in the same way as before, as we saw for the Fisher information, we can show that the quantum Fisher information measures the distinguishability of the two states which are parameter dependent, psi of x and psi of x plus delta x. Again, in the quantum world, the quantum Fisher information is a measure of the speed of separation of the states. And because of that, it's intimately related to the precision in the estimation of the parameter. In fact, we can show that the scalar product between these two states, psi of x and psi of x plus delta x, if delta x goes to 0, is given by this expression here. And again, you see the quantum Fisher information here, playing the same role that the Fisher information played in the classical situation when we consider the distance between true probability distributions. Here it is the distance between two states of the field corresponding to two different but very close values of the parameter. And this distance is measured by the quantum Fisher information. Okay? Now, the question then is how to get the quantum Fisher information. You know, from the definition I gave you, looks like a nightmare, right? You have to calculate the Fisher information and then find the maximum of that of all possible choices of POVMs, of operators. Now, there's a way of doing that, and that was developed by Hellstrom, Holevo, and you can also look at this paper, nice paper by Braunstein and Caves. Now, these people showed that the general expression for the quantum Fisher information can be written in this way here. This is the density matrix of the probe. It depends on the value of the parameter. That's the probe that goes to the dynamical system you want to investigate. And L is an operator. It's called symmetric logarithmic derivative, which is defined by this expression here. So if you can calculate this L here, then you find the quantum Fisher information. Now, for pure states and unitary evolution of the probe, one can find, and you can find that in these papers here, that the quantum Fisher information is given by a very simple expression. It's given by the variance, 4 times actually, the variance of this operator H, which is obtained as a function of the unitary evolution of the probe. Okay? So if you know the unitary evolution of the probe, you can find H, and if you find H, you can find the quantum Fisher information. Just as an example of that, suppose the unitary evolution is something like that. It's linear in the parameter, and this operator here is independent of X. Actually, it's the generator of the unitary transformation. Then you can show, using this expression, that in this case, H is just given by this O here. So if X is time, O will be the Hamiltonian, and you will be able to find uncertainties in time from the variance of the Hamiltonian. And this is just the delta E, delta T uncertainty relation. So from this expression here, we find, and from the Kramer-Rao relation, we find that the uncertainty estimation of the parameter is given by this expression here. That's the same Kramer-Rao relation, except that now I'm replacing the quantum Fisher information here by its expression in terms of the variance of this parameter. Now, you see, this really looks like the uncertainty relations, number phase or energy time uncertainty relations, but of course, it is not. It is not an uncertainty relation because X is not an operator, X is a parameter, okay? So that's the uncertainty in the parameter. X could be the phase, for instance, and in this case, H would be the generator of phase translations, as I'm going to show you briefly. Now, so this is for unitary evolutions. Now, if you have a noisy evolution of the probe, then in general, L is very difficult to calculate. Analytic expressions can be obtained from Gaussian states or low-dimensional Hilbert spaces, and I'm going to give you examples of that. Now, let me give you a simple example of the use of the Kramer-Rao relations in quantum physics. And the example I want to give you is the displacement, is of a displacement in phase space. You heard in the last lecture about phase space, so that example is within that framework. And you heard also about Wigner functions, so you should feel, I guess, comfortable with what I'm going to mention now. So this is the phase space, this is position, this is the momentum in this case, and this is the representation of a coherent state in the phase space. If you want, this is the Wigner representation, just a cross-section of the Wigner representation of a coherent state. It's a ball in phase space. Now, this is a squeezed state in phase space. And you see that the uncertainty in X here is smaller at the expense of increasing the variance of the momentum, okay? So it's a squeezed state. Now, suppose you want to make a displacement of the state in phase space. So you want to translate it in X. Now, this can be done by using this space translation operator, which depends on the momentum P. So P is the generator of space translations. If you apply this operator to the initial state of psi, you are going to have the final state of psi. You can see this here, so, okay. And you see that in this case, the H that I defined in the previous slide is just equal to the momentum. Now, the quantum Fisher information is now 4 times the variance of the generator. So it's equal to the average of the variance of the momentum. And the Kramer-Rao relation in this case can be written in this way. Okay? So the uncertainty in the estimation of the displacement is bounded below by the variance of the momentum in this state. Now, you see, this really looks like Heisenberg uncertainty relations, right? Between X and P. But as I mentioned before, it is not. X here is not an operator. It's a displacement. So in this exponential here, we don't have the product of 2 operators. We have the product of a number and an operator. So it's very important to keep this in mind. So, by the way, this displacement of a state in phase space was actually done experimentally in this paper here, which I collaborated with, that was done at Collège de France, and that was Serge Haroche's group. Now, if you have a coherent state here, then the variance in the momentum is equal to 1/2 in proper units. The variance of X is also given by 1/2. So you see that if you replace the variance in momentum here, you just get that the variance in X is larger or equal to 1/2, but we know that it must be equal to 1/2. So the coherent state saturates this relation here. This relation becomes an equality for a coherent state. That's, of course, the standard quantum limit because it's a coherent state, and the coherent state saturates Kramer-Rao bound. It's not unexpected because the Wigner function for a coherent state in phase space is a Gaussian. which you heard about in the previous slide, in the previous lecture. Now, you can maximize the variance of P in order to get better precision, right? That's what this expression says. So if I increase the variance of P, I will decrease the uncertainty decimation of X, and this is precisely what a squeeze state does. So if I translate this squeeze state, you see that this state becomes quasi-orthogonal to the initial one for a smaller value of delta X of the displacement. So that means that the uncertainty in the displacement is smaller in this case. So that's the trick to increase the precision. You just increase the variance of the generator of the transformation. Now, again, this looks like uncertainty relation, but X is a parameter, not an operator. I'll just skip this slide so as not to saturate you with too much information. And I'm going to jump to this slide here. So we consider the parameter estimation with noisy systems. And that's, of course, a challenge. The results are not so simple as the ones obtained for unitary evolutions of the probe and closed systems. Of course, if you have a Gaussian state, you can calculate it. If you have a system in a low-dimensional Hilbert space, you can also do it. But in general, it's very difficult to do it. So our idea was the following. Suppose you have some initial state and some non-unitary evolution of this state. So why? Because the system here is actually related to an environment. So it's not a closed system, it's a noisy system. So what do you do about it? Well, you do the following. You define in this closed system here, which involves the system of interest plus an environment, we define unitary evolution in the system, because now this whole system is closed. We call this a purification of the evolution. Of course, this unitary evolution must be such that if you trace out the environment, you get the correct evolution of the system S, which is given, say, for a master equation. And then you can show that the quantum Fisher information for the system S is bounded above by the quantum Fisher information of the whole thing. Okay, so why is that? Because if you consider the whole thing S plus E, you have more possibility of measurements than just looking at S alone. So if you have more choice, you can get a better precision. And that's the idea behind this. So by doing that, we get upper bounds for the quantum Fisher information of the system. And we have used that for lots of examples. I'm not going to describe these examples here for you, but we can show that this is actually very useful for getting bounds for the quantum Fisher information for noisy systems. The physical meaning of this bound, as I mentioned to you, is that the information obtained about the parameter when S plus E is monitored is larger than the information obtained about it when just S is monitored. And of course, we are interested in the least upper bound, which involves the minimization over all unitary evolutions in S plus E, which is a difficult problem. Okay, again, we have now a difficult problem. It's more difficult than the problem we found before, because you see, you have to find the best purification, and in this purification, the best measurements. Okay. Now we have shown in this paper here that the bound is actually attainable. There is always a purification such that this upper bound coincides with the quantum Fisher information of the system. And in fact, we have shown some examples in which the two coincided, and that allowed us to calculate exact quantum Fisher information for noisy systems. Okay? So we have been into this business since then, that was in 2010, and have applied this to many kinds of systems. I think it's a very useful approach. Now, I'd like to give you two examples, as I promised before, and we'll have time for questions afterwards. I told you that in some cases, noisy systems can be handled, and we can calculate the exact quantum Fisher information for them. This will happen if you have systems with low dimensionality, like qubits, for instance, dimension 2, or even entangled qubits, that's dimension 4. Okay, you remember that you can find the quantum Fisher information if you find that operator L, the symmetric logarithmic derivative. Now, if the dimensionality of this system is small, we can just diagonalize L, and we can find the quantum Fisher information. Okay, that amounts to diagonalizing a matrix. So let me give you an example, which I find it very curious, and we got some very interesting results from them. We consider a qubit could be a spin going through a channel which is a depolarizing channel. Okay, so you start with a polarized qubit, but then after it goes to the channel, it's not polarized anymore. It may be partially polarized, or it may be completely depolarized. Okay, partially polarized means that you don't know where it is in some region, or it may be completely depolarized. So this is called a quantum channel. Okay? It is a form of writing down the expression for an open system. The spin is depolarized by the environment. You may consider that the environment consists of lots of spins that act on this spin in order to depolarize it. And this channel can be written in a very simple way. And I'm just giving you an example of isotropic channel. In our work, we have also considered anisotropic channels as well. So the idea is the following. Theta is the probability of depolarization. And this expression shows that you have some probability that nothing happens to the density matrix of the spin. And then there is some chance that there is some error, that there is some depolarization. Now, in this expression, we have here the Pauli matrices or Pauli operators. I put a hat on the symbol to say that it is an operator. That's the density operator of the probe. And these Pauli operators represent all possible errors in the transmission of a spin to the channel. How can we describe these errors? Sorry. So sigma 1, for instance, is the sigma x Pauli matrix. And when applied to the density operator of the probe, it leaves the x direction unchanged, but it transforms the z and y components of the spin. So this is the so-called Bloch sphere for a spin. It shows the several directions where the spin can be. It's a sphere, radius 1. And then if you apply this sigma x to it, this sphere gets compressed like this one. You see, this is the x-axis here. This is the y-axis. The z-axis is vertical. So the x, nothing changes along the x-axis, but the things change along the y-axis and the z-axis. So that's the so-called bit flip. The sigma x spin operator changes a spin which is pointing up into a spin pointing down. Okay, it's a rotation, if you want, around the x-axis. Now, this is so-called phase flip. This is sigma z Pauli matrix. This Pauli matrix does not change the z-axis, but it does compress the x and y-axis. So this sphere gets transformed into this ellipsoid here. Okay? So sigma z affects the phase of a spin. If you have a spin in some direction, it will make it rotate around the z-axis, say, because the phase between the up and down component will change. And sigma 2, finally, is the sigma y Pauli matrix. This is the so-called bit phase flip. It produces a flip of the spin, but also it changes the phase. The y-axis remains unchanged, but then this ball here becomes this one. So this is 3 kinds of errors that can affect the spin, and this isotropic channel consider that all three of them happen with the same probability, and the probability is given by this parameter theta. What do we want to do? We want to use the probe, which is a spin, to estimate what is the probability of depolarization. Okay? So I'll just give you the results. In this case, we have, if you just have a spin, you have a very Hilbert space with a very small dimensionality. If you have two spins, the dimensionality is 4. It's also very simple to deal. So we can actually solve this problem explicitly and calculate the quantum Fisher information. And this plot gives you the quantum Fisher information as a function of theta, the depolarization parameter. Just remember that the higher the larger the quantum Fisher information, the better will be the precision in the estimation of the parameter theta. Now, we consider here 3 kinds of situations. One situation is just sending the spin through the channel. In fact, we can send 2 photons through the channel. We want to keep the number of probes equal to all the 3 possibilities. So we may change 2. We may send 2 spins through the channel, or we may send 1 spin through the channel and the other outside the channel, but the 2 are entangled. Very interesting situations. You see here, only 1 spin probes the channel. The other does not probe the channel. So you might wonder, okay, is this different from just having 1 spin probing the channel? And I'll show you that it is quite different, and that in fact entanglement helps. So we take as initial state of the 2 qubits, in this case, a state like this. It's a superposition of both up and both down, okay? And this is the initial state. And then we send the spin through the depolarization channel. This one follows. And then we make a global measurement on the 2 spins. That is, we project the final state onto the initial state in its orthogonal space. Okay? We show that that's the best possible measurement. And then what we get, I find very amazing. Let me tell you what this plot means. By the way, this paper is submitted for publication, okay? And you'll be able to see it soon or not, depending on the referees. So these are the results. This green curve here, can you see it? That's when I send 2 independent spins to the depolarization channel. This can be described by a product state of the 2 spins, okay? 2 spins sent to the channel, product state. This blue curve here, I find it amazing. It's when I send 2 entangled spins through this system, but only one of them goes to the depolarization channel. And finally, the orange curve here corresponds to sending 2 entangled probes like this one through the channel. Okay, instead of having one going outside the channel, we send both of them, but entangled through the channel and project onto this initial state here. So this is the result. You see, as theta increases, that means that the depolarization increases. So theta equal to 1 means complete depolarization. Just look at this expression here. Theta equal to 1, you just don't have this term here, which represents the initial state, and that means complete depolarization. Theta equal to 0 means that this term vanishes, so you have just the initial state of the probe after it crosses the channel, so no depolarization at all. So you see that for strong depolarization, probe plus oscilla is better than all other possibilities. It's better than the product state. It's better than sending the 2 entangled probes through the channel. Now that I find that very interesting. That shows that, sending this spin outside the channel, by the way, it's called an oscilla. It's an auxiliary spin, makes the measurement much better than just sending the 2 spins unentangled through the channel. And I find this result very, very nice. Also, for weak polarization, then you see that the orange curve wins, but not for so much like this one. This means that for weak depolarization, it is better to send two entangled probes through the channel instead of sending two separate qubits or even a probe plus oscillator. But I find, this part of the curve very nice. It shows that if the absorption is very large, it's better, not to send it to photons through the depolarization medium. You just keep one outside. Sort of, you are protecting it from the depolarization, and then you measure both things. Now, what we have shown is something interesting. First, that if you send two separable photons in a separable state, you just get the same result as if you just send them one photon to the channel. So that's one point. The second thing that we showed is that if you don't project them on an entangled state, you don't get this quantum advantage here. So making this entangling measurement is very important for getting the correct result. What we have shown, in fact, is that if you send separable states, they always lead to a quantum Fisher information bounded above by an average of quantum Fisher informations corresponding to single probes. So the initial entanglement is here essential for quantum gain. Now, there is some similarity here with quantum illumination. I'm not going to describe this to you. It's somewhat beyond our lecture here. So just stay with these results here. We can show that, when you go into this region where the probe plus ancilla leads to quantum gain, this is precisely the region when the two spins are unentangled at the end. So depolarization has destroyed the entanglement, but even so, projecting them onto this state leads to this gain here. So the entangling measurement helps us even when the two outgoing states are unentangled. And I find these peculiarities of this example very interesting and very nice. Finally, final example. Suppose we want to estimate the absorption of some channel. We have some substance, some liquid, some gas, and we want to estimate the absorption of light from this substance. Classically, we can send a light through it, and then we measure the intensity of light, of the outgoing light, and from this measurement of the outgoing light, we can find what this absorption is. Now, what we have shown is that we can get a significant quantum advantage by using this system instead. And again, we have here entangled states, and we have an ancilla approach. This is an optical parametric amplifier. Now, I'm not sure you know what an optical parametric amplifier is, so let me try to describe it in simple terms. This is just a system that, it's pumped by some laser here, these two, and even with zero input from this side here, it produces two beams. In fact, it produces a Gaussian state at the end, which is a squeezed Gaussian state, but it's a Gaussian state of two modes. And it produces two beams that are entangled. So again, you send one of the beams to the substance that has this absorption coefficient. The other beam goes outside this medium, and then you apply to these two beams the same optical parametric amplifier inverse. That means you change the phase there, so that if you did not have this substance here, you'd get at the end vacuum as here. In other words, this optical parametric amplifier eliminates the squeezing produced by this one. So at the end, you have vacuum. If you put some medium inside, you don't have vacuum, you have a signal. So you see, this is a strategy to zero the signal if you don't have any medium inside, okay? You squeeze here, you destroy the squeezing here, and you get vacuum here. But if you have alpha here, if you have a medium with some coefficient of absorption, you get some signal here. And again, you should do a global measurement here. You measure the number of photons outside, simply that. And this is also submitted for publication. It's a collaboration with Ruiné Matos Filho, my colleague at the Federal University of Rio de Janeiro. Girish Agarwal, who gave a lecture here in this conference, he's at Texas, and Wang is a student of Agarwal. Now, so we call this, time reversal, because we unsqueeze the field that was squeezed by this first nonlinear device. Now, let me show you the results we get. We can calculate the quantum Fisher information. In this case, it's a Gaussian state. And then we find the following. This green curve here is the result of this classical calculation. We consider just the limit of classical fields. There is a coherent state coming here and a coherent state outside. We measure the intensity outside, compare with the intensity inside, and then we find from that the coefficient of absorption and the uncertainty in this coefficient of absorption, which is given by this expression in the classical case. Okay? Now, in the quantum case, the situation is more complicated. I'm not going to give you an expression, which is a huge expression, but I will give you the curve. And these are the curves for the precision in the estimation of alpha. And you see, this is the time reversal approach that I showed you before. The two nonlinear devices, one squeezes, the other unsqueezes, and then the absorption medium is between them, and then you measure the number of photons outside. So this is the uncertainty in the absorption coefficient you find using this device here, and this is the classical result. Now you see the gain you find in the precision here for an average number of photons equal to 10 is equal to 5 decibels, which is very nice. Now, you might ask, come on, why don't you just increase the average number of photons in the beginning? You see from here, if you increase the intensity in the beginning, you decrease the precision. So you might as well use classical means and just increase the intensity. Well, you cannot do this sometimes. For instance, if you want to estimate the absorption of biological samples, you cannot increase the intensity too much, or if you do that, you kill the sample. So this is very useful for media that must be probed by weak intensities of light. With the same intensity, using the classical approach or the quantum approach, you get a fantastic gain in the precision of estimation. Now, that was my last slide. I just want to show you some of our work on quantum metrology. This is the work I mentioned before. It's a general framework for estimating the ultimate precision limit in noisy quantum-enhanced metrology. These are some applications of this method. We have looked at quantum speed limit for physical processes. This is delta E, delta T relation from the point of view of quantum metrology. We have looked at the measurement of a small microwave field amplitude injected into a cavity and beyond the standard quantum limit. This was an experiment made at Haroshi's group, and you can read it at this issue of Physical Review. It's the displacement of the field in the cavity that is measured, and we got some very good result using all these apparatus of quantum Fisher information and so forth. This is a paper in collaboration with Girish Agarwal. Maybe he talked about it here, I don't know. It has to do with some experiment which was done by the group of David Wineland. This was an experiment made in Rio de Janeiro, quantum enhanced sensing from hyperentanglement. You see, we even have hyperentanglement there. That means entanglement between the polarization degrees of freedom of the photons, but also between the momentum degrees of freedom. And we show that that can enhance sensing. And these are two submitted papers which I mentioned before. So I should acknowledge my collaborators in this area of quantum metrology. At the Federal University of Rio de Janeiro, we had some very nice students who helped a lot to get these results. Some of them are professors now in several institutions. These are my colleagues. These two here are experimental colleagues. They are taking care of the quantum optics lab in the Institute of Physics of the Federal University of Rio de Janeiro. And these three professors here are theoreticians. And we have a tradition now in our institution of strong collaboration between people who do theory and people who do experiments. And I learned that by collaborating with Serge Haroche's group at Collège de France. There also the relation between theory and experiment is very close. And we have that now in Rio de Janeiro. And I should acknowledge also the collaboration with Girish Agarwal at Texas A&M University. And as you know, of course, Girish is an amazing scientist, and the collaboration with him was precious, has been precious for me. So that's it, folks. Thank you very much for your attention. I'm ready to answer to your questions.
So thank you very much, Professor Davidovich, for this excellent talk. And now we will take up some questions, I hope. So if there are questions, let me look at the chat box. There are none. Anyway, so while waiting for the first question, let me just try to ask you, among the very two interesting examples that you showed, if you can, try to learn something which is common to these experiments. So my question is, in the first one, you showed that if your parameter, that is the depolarizing parameter, is very large, then this probe plus ancilla strategy works the best. Now, in the second experiment, if I'm not mistaken, the corresponding parameter is the absorption coefficient, isn't it? So right. if I increase the absorption coefficient, are you able to show that the strategy works better or not for this case?
Well, yeah, okay, very good question. In fact, this strategy gets better for weak absorption in this case. Okay. So very good question, and because I did not mention that, that's why in the example I showed you, alpha was 0.05, I guess, something like that. Okay, and I contacted some experimentalists, friend of mine, actually at Texas A&M, and they showed me that usually, the absorption coefficient of substances, biological substances they're interested in, is much smaller than 1. So you really need a very high precision in that case.
Okay, so thanks. Yeah. So, but in this respect, the physics of these two, different things. One in the case of depolarization and the other different is a slightly different because the strategy is common, but in one case it gives advantage for a different range of parameters.
That's true. Very much so. That's true.
So it will be interesting to understand what is the underlying, reason or physics behind
That's
such
true.
an advantage.
I agree. I agree with you. In the case of sure, I agree with you. In the case of the depolarization, we have some intuitive understanding. Of course, if you have a strong absorption, it's intuitive, but it's not completely correct. It's very tricky, but it's like that. In the case of strong absorption, you see the ancilla approach was very good, right? And the idea is that strong absorption, the ancilla allows you to sort of protect one of the qubits from the action of the depolarization channel, okay? So you get better sensitivity in this case, okay? Now, in the absorption case, it's true that you get, one gets better precision in this for the two nonlinear devices in the absorption case, but that's really related to a trick. And thank you for this question, because then I will be able to say what the trick was. And the trick was the following. Instead of having the second OPA, I could do it another way. After the first one, I could measure jointly the ancilla and the photons that have gone through the medium, the absorption medium. Right? It's a joint measurement, which means that I'll be measuring something like P index NM. Is the probability of measuring N photons in one beam and m photons in the other. Okay, it's a joint measurement of photon numbers. And if I do that, then our approach will be good for any absorption. Okay. Now, the problem with that is that it's very difficult to make these joint photon number measurements for all kinds of photon numbers. And so that's why you have the second nonlinear device. And that gives me the same result as the joint photon number if the absorption is small. If the absorption is large, they do not coincide anymore. So that we have to go to the joint photon number approach. And that, again, my experimental colleagues say it's tough to do. Okay, it's tough. Even nowadays we can count photons with special detectors, but making joint photon counting is tough.
Yeah, sure. Thanks. I mean, it's so amazing how many interesting techniques you're working out. And as you showed out, there are so many applications which need such techniques these days. I mean, in various branches of not only physics, like say gravitational waves, but also in biological processes and many different processes of importance in society.
That's
so,
right.
Yeah. So, are there any questions? Let me see from the participants, mostly students we have now. Of
Someone
course,
has the hand
raised a hand.
Yes, sir.
Yeah, please go ahead.
Am I audible?
Yeah, you're audible. Yeah, please go ahead. Yeah, please go ahead.
Yes, sir. The phase space which you had described of the phase difference and the operator P. Over there, is there any underlying geometry in that phase space? And can that geometry be influenced by the eigen operators of the state psi?
Okay. Let me see if I understood the question. You are talking about the estimation of phase, right?
Yes.
Okay. Now, and in fact, you see, if I don't answer your question, because I'm not sure I have completely understood it, you tell me, okay? You ask it again, but let me try to reply it in the way I understood. So, in fact, I think I can reply it in a way which maybe will answer your question. See, in that situation, I have compared the two coherent states, right, in the example I gave, and I showed that if you want to have them distinguishable, then you have the standard deviation for the phase, right? Okay.
Yes,
now, if you treat that with the quantum Fisher information, and I just skipped that slide, actually, if you allow me, I will just go back to that because I skipped the slide that has maybe the answer to your question. Yeah, so you see, so this is the same calculation which I have done last time, comparing alpha with alpha e to the I theta, okay? But here it's given by the quantum Fisher information. I know that the generator of phase displacements is a number operator. If you apply, for instance, this exponential here to this coherent state alpha, you get this state alpha. Okay? So the quantum Fisher information will be given by the variance of this number operator. And now you can play with that. That's the phase relation. So the uncertainty in phase is given by this expression. That's the Kramer-Rao relation. And here, n plays the role of the h I defined before, okay? So that's the generator of phase translations. Now, if you have a coherent state, the variance is given by 4 times, is given by the average of n. So if you just replace this result here for a coherent state, then you find the standard limit in this case, which is 1/2 square root of the average of n. But you see, and I think that relates to your question, before, when I compared the two coherent states, I found that the lower bound for the uncertainty was 1/square root of the average number of photons. Remember that?
Yes, sir.
Now using the quantum Fisher information, I'm getting this factor 2 here. So I'm getting a lower bound than before. And that, I think, is related to the question, because when we get that from the quantum field information, we immediately have to think, maybe there's a better way to measure this phase than just comparing the two coherent states.
Yes,
okay?
yes, sir.
And indeed, there is a better way. You can show that, instead of there, we are comparing the coherent state with a displaced coherent state. Now we can do a homodyne measurement of the state that goes through the interferometer, and that will give you a better result. Okay, so I welcome your question, but because that gives me the chance to show this example that shows that the quantum Fisher information is very useful for experimentalists as a benchmark. It shows that come on, instead of comparing the displaced phase coherent state with an undisplaced phase coherent state, you can do better. You do a homodyne measurement of the coherent state and you get a better bound. Okay, so indeed you can show you can choose different measurements, and the best measurement will get you the quantum Fisher information. Now, geometrically, sometimes you can find what are the best measurements. For unitary evolutions, it's easy, as I have shown. It's just given by the variance of this H operator, of the transformation. But for noisy systems, unfortunately, we don't have up to now any way of doing this, say in a geometric way or something else to find the best measurement. So one way is, like I showed you, to expand the space. Other people have proposed other ways of doing that, but we don't have a general way of finding analytic solutions for that. I'm not sure I answered your question. If not, please insist. Ask it again.
Yes, sir, that's what I asked. It was approximately, yes.
Okay, so let's move on to there's another question by Ranjit Singh. So let us,
Thank you for your talk. I have two questions, so I don't know whether I have time. So the first one is, on your slide, estimation of absorption, in one OPA, I think that spontaneous parametric down conversion process is going when two photons are in vacuum state. But in second OPO, two photons are present in two modes. So my question is, what process you are using at second OPO? Some frequency generation or spontaneous parametric down conversion? In this case, it should be not spontaneous parametric down conversion, I think.
Very good. So no, actually, in the first optical parametric amplifier, we are not using spontaneous down conversion. Okay, it's an induced process. You have a beam, a laser beam, which is pumping the nonlinear device. So this is related, if you want, to four-wave mixing. It's a nonlinear process, and it's not spontaneous down conversion. And the second OPA does the same thing. It's like a four-wave mixing, and so it's a nonlinear process. But there's some phase that we change the signal of the phase. You can do that with the pumping laser. So the process there is the inverse of the initial process. So that's why you can do it. Okay.
Okay.
So it's not spontaneous; it's induced.
Mm-hmm. Thank you. Second question: delta n and delta phi expression. In this expression, did you consider phi as a phase operator?
Okay, very good. No, I have not. Okay, and that's actually an important point in this presentation. Some people have defined phase operators. Many people have done that, and with that they build a phase number uncertainty relation, which is something that you find here in this expression. Let me again share this slide I had as I did before. Just a moment. Yeah, so that's the slide I wanted to share. Oops. So you see, you could consider this expression here, can you see with the pointer is showing it, huh? As a phase number uncertainty relation, okay? Because this will be the variance in theta, this is the variance in the photon number, okay? It's the square root of the variance, so this is the uncertainty, the photon number, the square root. So this is delta theta, delta n, larger or equal to 1/2. Huh? So it's like a phase number uncertainty relation. However, we are not considering theta as coming from an operator. Theta is a parameter, which is just this phase, okay? And this is not the Heisenberg uncertainty relation. This is the Kramer-Rao uncertainty relation. So I think one of the beauties of this approach is that we don't need a phase operator in order to have a number phase uncertainty relation. In the same way that we don't need a time operator in order to have an energy time uncertainty relation. You know, maybe you know that the question about time operators also is a long-standing one. People wanted to interpret the delta E, delta T uncertainty relation as coming from a time operator, and it was Wolfgang Pauli that showed that that would be impossible, because if you have a relation between energy and time with a time operator, that means that time would be a generator for displacements in the energy, in the same way that the momentum that satisfies a Heisenberg, that satisfies a commutation relation with X would be a displacement, would be a generator of displacements of the position. So if you have time as an operator, then you would be able to displace the energy of the system indefinitely, up to minus infinity. So the system would be unstable. Okay, that was the argument of Wolfgang Pauli. So there cannot be a general time operator, because this would lead to unstable Hamiltonians. You can lower the energy as much as you want just by displacing the operator. Now, so in our case, again, time is a parameter. And I have not discussed this time energy uncertainty relation here, but time is a parameter. So we don't need a time operator. We just want to estimate the duration of a process given some variance of the energy of the system. So that's our approach. And I think that's the more correct approach, instead of trying to define a phase operator, because, you know, it's possible to do it in several ways, but, you know, there is always some trick, some special situation, and here we don't need that. So phase for us is a parameter.
Thank you.
Okay.
So yeah, thank you very much once again. So if there are no further questions, let's thank Professor Davidovich once again for the wonderful, very nice, excellent talk, and for sparing his time to be with us to answer our questions. And we wish you a very pleasant day, and thank you so much. And so before concluding, it's my pleasant duty to thank all the three speakers of this session: Professor Kasla Bruckner, Professor Subhash Chaturvedi, and Professor Luiz Davidovich. So thanks to you all. Thank you very much. Bye.
Thank you very much, Professor, for the invitation. I'm very glad to participate in this conference. Thank you, and have a good evening. Have a good evening.
Thank you so much.
India.
Thank you.
Bye.
Thank you so much. Bye.
Thank you. Bye.
Bye.